Hey guys, so I just wanted to go through the conceptual physics chapter 7 worksheets with you for a moment. A couple concepts that are a little bit difficult to understand without me explaining them. So when you put something in water, it has a certain volume or amount of space that it takes up. Okay, and so if let's say you put a 1 liter bottle into a glass of water or a bowl of water, it takes up an amount of space that is equal to 1 liter. All right. Now, 1 liter of water, if you were to take that liter of water and put it on a scale, it would have a certain amount of weight. So whether or not something floats or not is going to be dependent upon the amount of water that it displaces or the amount of water that it moves. All right. So when we talk about looking at the first one, Archimedes' principle, right? A balloon filled with a liter of water, 1,000 centimeters cubed, in equilibrium in a container of water as shown in figure 1. What is the mass of the 1 liter of water? All right. Now, 1 liter of water, water's density is 1.000, right? So 1 liter of water would be 1 kilogram, because if you will, the mass divided by the volume, okay, the mass 1 kilogram, 1,000 grams, divided by 1,000 centimeters cubed, right, is 1. Also 1 kilogram over 1 liter, okay? So what is the weight of that liter of water? Well, in our class, we have moved the gravitational pull to 10, all right? We've just rounded it up, but technically it would be 9.8 newtons, right? Because 1 kilogram times 10 or times 9.8 would be 9.8. Now, if you put 10, that's fine. So the weight of the water that's displaced would then be the same weight, because water has the same density as water. So the weight of the water displaced would also be 10 newtons, all right? And the buoyant force, right, that is the force that allows something to float, would also be 10 newtons, okay? So whether or not you and I float, whether or not a piece of wood floats, is directly related to the amount of water that it displaces based on its weight and the volume that it takes up. So a rock, let's say a small rock, right, has a small volume, but it has a high mass. So if you put it in the water, the amount of water that it moves is going to weigh less than the weight of the rock. Therefore, the rock will sink. But in a piece of wood, the amount of water that it displaces is actually heavier than the weight of the wood. So the wood floats. Okay? Moving on. I'm moving to the second page. You can see a similar drawing where you have in figure 2, question number 3, 1,000 centimeters cubed is the volume. Okay? So what volume of water is displaced by the wood? All right, the volume of water is 1 liter. What is the mass of the water displaced by the wood? Right, so 1 liter of water weighs 1 kilogram, as we learned before. Okay, so the weight of the water would then also be 10 newtons. Right, therefore the buoyant force would be 10 newtons. All right, so if the hand is removed, what is the net force on the wood? The net force is equal to the buoyant force, right, minus the weight of the wood, okay? So in the picture, you can see that the weight of the wood, so the buoyant force is 9.8 newtons or 10 newtons, okay? And you would subtract the weight of the wood, okay? In which case, we're saying the weight of the wood is 4.9 newtons the weight of the wood is 4.9 newtons, so if you will, 10 newtons minus 5 newtons, you would have 5 newtons of upward force because of the weight of the wood. All right? I want you guys to look at the bottom of page 52, where you can see the rock in the picture, where you see the rock, it says the rock is 5 kilograms, so you would know that the weight of the rock is 5 kilograms, and if it takes up 1,000 centimeters cubed, or a liter, then we know that the buoyant force, because the volume is 1 liter. The buoyant force of 1 liter is 10 newtons. Now, a 5 kilogram rock exerts 50 newtons. So if you had the 10 newtons of buoyant force minus the 50 newtons of the rock, then you have a negative 40 newtons, or otherwise it's going to go 40 newtons downward. That will be the speed that the rock sinks in the water. Moving on to page 53, the next one, Archimedes Principle 2. You have 6 different pictures of blocks, and based upon how far the block goes under the water, right, you can see whether it's buoyant, right, or not. Okay, so the first one, it is just denser than water, so it sinks. The second one is the same density as water, so it will not sink and it will not float. It just sits wherever it is. So if you put it to the bottom, it wouldn't float up and it wouldn't float down. But if you put it up higher, it will stay wherever it is. The next one, half as dense as water, right? So you would want to, you have these blocks, you'd want to show the water line to be halfway of the block, okay? And then the first picture on the bottom, you would show a quarter of the water is a quarter of the way up the block. The next one, 3/4 of the way up the block, so only the top quarter is above water. And then if it's open, right, the water would fill it up, so it would have the same density of water, but it would sink because of the actual block. Now down at the bottom, when you look at different ships, right, you see the ship's displacement of water is a certain weight, so that means that it pushes down to a certain amount, but when you load the ship with iron, the ship goes lower, or if you will, it sinks deeper, okay? But you have to understand, it's based upon the weight of the ship. So if you put 50 tons of iron or 50 tons of styrofoam, they're going to sink the same place. Why? Because 50 tons is 50 tons. It doesn't matter what the material is. Now, 50 tons of styrofoam would take up much more space than 50 tons of iron, but they still are the same weight, but the styrofoam takes up a whole lot more space. Okay? In our last 2 pictures, you have an ice cube floating in a glass of ice water, right? If you're drawing the water line after the ice cube melts, okay, you have to understand that when the ice melts, right, the weight of the ice pushing down on the water pushes up the water line. So when the ice melts, and if you will, it has more water, or it takes up less space, then the water line will then be the same because it still has the same weight pushing down, therefore raising the water line. So essentially, when we're trying to find out a buoyant force, whether something floats or not, it is based on the density. So if it is less dense than water, it'll float. If it is more dense than water, it will sink, okay? And based upon how dense it is will determine how fast it sinks, okay? But when we talk about the density, we're talking about the amount of space that something takes up based upon the amount of mass that it has, right? So when we talk about density, we're talking about mass over volume. So if something has a greater volume in the same mass, right, it has a lower density. But if it has a greater mass and a lower volume, then it has a higher density, okay? So it's very important to understand that. And then lastly, talking about gas pressure on page 55 worksheet. A principal difference between a liquid and a gas is that when a liquid is under pressure, its volume does not change, right? Okay, so you cannot take a bottle of water and you cannot compress that water. However, if you have oxygen, you can compress a lot of oxygen into a tank, okay? Once you fill up the tank with water, you cannot stuff more water in, but gas is what we call compressible, all right? So also, when a liquid is in under pressure, you can't change its density because you can't change its mass, you can't change its volume, so it has to stay the same size, so its density remains the same. But when a gas is under pressure, right, its volume shrinks. Think about a tank of gas. If you put oxygen in a tank of gas, the volume is limited to that tank of gas. If you let it out of that tank of gas, the oxygen will spread in the atmosphere and it will take up a greater amount of space, all right? And the density, of course, if you pack oxygen into a smaller space, you have the same amount of mass, but taking up a smaller amount of space. So therefore, if you decrease the volume, you are increasing the density. Okay? So there's the top of page 55. You can continue in 55 using that knowledge and understanding that you learned, that you got from that. Please, if you have any questions, let me know about these worksheets, and you should be having them in to me by tomorrow.